My name is Stefan Kubarik. I'm professor here at the University of Graz and an ESAF user since 2004, so for quite some time. I'm part of the ESAF user organization headed by Guillaume Morat. And the user organization committee is there for ESAF users to collect feedback from users. We organize things such as this webinar series, which you can also see on YouTube. So you can subscribe to the ESAF YouTube channel. And importantly, our task is also to organize the ESAF user meeting, which this year is from the 10th to the 12th of February. A reminder that this Sunday, 19th of January, is the deadline if you want to register for the user meeting. I'm very happy to introduce today's speaker, Oleg Konovalov. He has been at the ESAF for a long time, but let me start with his scientific CV. He started as a junior scientist at the Institute of Crystallography of the Soviet Union, at the USSR Academy of Sciences, and looked at 2D, 3D crystallographic problems, was developing software for reflectometry at the Academy of Sciences in Moscow. He did some very early work on reflectometry and grazing incidence diffraction of Langmuir blotchet films, and started working in Grenoble as a visiting scientist in 1992, where he studied phase transitions of 2D crystals of fatty alcohols with X-ray techniques, but also ellipsometry. He got his PhD in 1996, and after a stay as a postdoctoral researcher at the Atomic Energy Commission in Grenoble until 1999, he joined ESAF, and since then is a beamline scientist and first postdocs and beamline scientists there. And in 2004, as a very young PhD student, I was very happy that my very first experiment at a synchrotron ever was at Oleg's beamline, and I learned a lot back in the day, and I'm still learning things today. So I'm very much looking forward to Oleg's talk. Thank you.
Thank you, Stefan. So good afternoon, everybody. So I'm happy that you're present to listen about ID10 beamline. So then my talk will be quite, let's say, general and open about ID10 surface scattering end station. Here you can see our main configuration with the Langmuir trough, and I will tell more details later. And then my talk will be basically from three big parts, like first, general introduction to ID10 surface scattering beamline, then the available sample environments what we have at the beamline for users, and I will present our experimental technique with some scientific examples. So then, first of all, what I should say about ID10, that ID10 beamline, this is a double end station instrument with a at the soft interface and coherent scattering beamline in the complex system and the biomedical surface science group. And we have two end stations. One is surface for the surface scattering, which is upstream station. So then I can, okay, sure. So then this is this one. And the second one, which is a bit blued here, this is a second station for coherent scattering. But today I'm not talking about this. So all the talk is only focused about surface station. And then what users should know in general that these two stations, they are working in a time sharing mode. So then half of the beam time is used for the surface and half of the time for coherent applications. And then we're working in this regime from 2012. So now, first, the few words about the surface scattering techniques. So then what we, how it works in general and what we can learn out of that. So then if we want to discriminate the scattering between the surface and the bulk, So then how to do this, that we have majority signal from the surface. And for this, we use very interesting feature of the X-rays that they have a index of refraction, which is smaller than 1. And then it means that we have a small angles where we are below total reflection from the surface, where penetration of the X-rays in the material is very small. Then it could be controllable depending on the grazing angle. So this is a geometry that we have a surface, we have a beam which goes at a very shallow angle to the surface, and then afterwards we scatter. And then by changing this angle or working below the critical angle, we can probe only very top layers of the system, and then like this we can see what is going on the surface, compare with the bulk. But of course, if we have something deposited on any type of substrate, also with the same technique, we can probe only this film. So then playing difference in the scattering or critical angles, we can magnify intensity from the surface. So then there are basically, let's say, two big types of measurements when we can measure signal in the plane of the incidence, or we can measure signal in the plane of the sample. So then when we measure signal in the plane of the incidence, and the angle of incidence and the exit angle measurement is the same, so then this is all called X-ray reflectivity. In this case, scattering vector is normal to the surface, and then we can analyze the electron density profile along the interface. And then from this profile, we can learn something like thickness of the film or sample density, also the roughness of the film. And then if we measure in plane of the sample plane, so then grazing angle is very small, so to below the critical angle, and we measure all the signal which comes out in Q Z and Q parallel. So then in this case, we this is the physics is the same, but we can distinct like two methods. Measure in a small angle regime, so-called grazing-incident small angle scattering, or grazing-incident diffraction, or it could be also grazing-incident wide angle scattering. So then nowadays, when people more and more work with nanoparticles, so then these two let's say regimes, they can merge together, because we work in a small angle regime, but we measure diffraction because we see how the some units they ordered in space systematically. So then it's also we may measure back diffraction in a very small angle, like in Sachs regime. But historically, it comes like if we measure at a small angle, this is G-Sachs, and then we can get information about particle geometry, size distribution, partial correlations, and on nanometric scale. And for traditional GID, so this is big angles, so then we can see diffraction from two-dimensional systems. And then in this case, we can see what is the lattice parameters. But if we have macromolecules or rod-like molecules, we can learn also about the structure of the molecule, or tilt angle of these molecules, or tilt preferential direction of the tilt of these molecules. And additionally, if we will measure the fluorescence signal coming from the surface, so in this case, we can probe at a near interface elemental profile. So then also to see electronic structure of the atoms of elements near the surface. And here as well, by changing the angle, we can change penetration depth, and then we can excite atoms at a different depth of our film, and then measuring with detector the fluorescence signal, we can also to see not only which atoms near the interface, because here we can see really the elements. So X-ray reflectivity is sensitive only to the number of electrons, but not to which atoms this electron belong. But with the fluorescence, each atom has its own fingerprint pattern, so then we can discriminate it. Then by increasing the penetration depth, we can excite more and more deeper layers of atoms, and then from these curves, we can get information about the distribution of these elements near the surface. So then this is a general picture slide of what we can measure. So with all of these techniques which I just mentioned, and we can apply all of this to different type of interfaces. This could be solid liquid interface, liquid-liquid interface, gas-liquid interface, or of course solid gas. This is very easy in this case. And also additionally here, recently we start to apply Xanis measurements near the interfaces, and then like this to see what is electronic states. And several big, let's say, topics which we cover at the beamline with in-house and external user experiments. This is biomimetic systems using the language graph, and then we can make a kind of a cell membranes and see interaction of this membrane with different molecules, with proteins or with peptides or some other agents. So then we do a lot of studies with two-dimensional materials which build from atoms, molecules, or macromolecules. So the chemical reactions, we can look some catalysis also. Then we study a lot semiconducting polymer films, different type of surfactants. And then here, this is some examples of linear films on the liquid surface. That is how element analysis works. So buried interfaces for the nanoparticle organization, or another type of nanoparticles where you can see simultaneously a lot of information in different scales in real and reciprocal space. So a few words about the general beamline layout. And here only I will point out the important things to know. That first of all, as a source, we have three undulators, two stationary undulators, U35 and U27, and one revolver which holds U35 and U27. So then like this, we can either make 2 times 37 and 35, or 2 times 35 and 1 27. So like this, we can play a lot with intensity. And here, this is the spectrum which this undulator gives. So red is 27 and blue is 35. And from here, you can see immediately why we need 35. This just cover the gap what we have for U27 undulator. But U27 gives much more intensity. But if some experiments need less intensity, but especially the beam within the range in this gap, so then we can apply U35 undulators. And afterwards, we have a horizontally oriented mirror with the different coatings, palladium, silicon, platinum. This is to work at the different energies. And then we have a monochromator with a channel cut crystal. And there are possibility to work either with silicon 101 channel cut or with silicon 301. So then again, this depends on energy which we want to use, and also with the bandwidth after the monochromator. And our typical range of measurements where we can work, this is between 7 and 30 kilo electron volts. And when the beam is already monochromatized, we can focus it on the sample or on detector. So it depends what we want, but usually we focus on the sample. And then in this case, we use the transfocator. This is a beryllium compound refractive lenses with a radius 300 microns. And then we can set from 0 to 63 lenses. And like this, we can focus each energy at which we work at, or any energy on the sample with 10 micron beam vertically and 35 horizontally. This is 4:1 focusing scheme. So also we have another transfocator which is closer to sample, and then it can focus with 11 to 1 ratio. And afterwards we go to the experimental hatch. And here what I want to show on this slide, that we have on sample like 10 to 13 photons per second at 200 milliamps. So then this is quite big intensity in this small size of the beam. And then we have inside a deflector to deflect the beam down to the liquid surfaces, and the diffractometer. And here you can see it a bit more in detail, what we have in the experimental hatch. So before, at the beginning of the hatch, we have a fast shutter. So then fast shutter is needed to stop the beam when we don't measure. So like this, we protect sample, and also we protect detectors. Then another element what I already mentioned, this is a double crystal deflector. When we work on liquid surfaces, but majority of time we work on liquid surfaces at this beam line, so then we need to tilt the beam. And to tilt the beam, so X-rays, it's not trivial to tilt the synchrotron and not trivial to tilt the liquid surface. So then we need to tilt the beam. And then for this, we have this special device, what we call double crystal deflector. And how it works, I will tell you a bit later. And then we have a diffractometer with a detect arm, which can hold several detector schemes at the same time. And then we can measure what I showed previously, different type of measurements like reflectivity, GSAX, GVAX, and the fluorescence almost simultaneously on the same sample, which is very useful to get a complex of characterization of the system at the study. So then we can install also the long flight tube and then walk up to 4 meters from the sample to detect and then to do high resolution for the almost submicron size particles organized, or to have better resolution in real space for the system. And we can apply different type of detectors. As I say, as we work at the same time with different technique, we also have at the same time working several detectors, and then we have zero point detectors. So this is still the counters, engine chambers. We have one-dimensional detectors like Myton detector, and also we have 2 detectors, different type. Majority of them is cadmium telluride, like MaxiPix, Eiger, but also we have silicon detectors. And this is a view of diffractometer in a way when we don't use DCD. So then the beam just goes through the flight tube. We have monitoring system, slits, and attenuator wheel. So then attenuator is used to also change intensity of the beam on the sample. So for one side to protect it, but also to have a beam which is digestible for detector, that detector works in a linear regime and doesn't saturated, so that we can measure. And also here you can see that this is our detector arm, which can hold different detection schemes. So on this image, this is 2. One, for example, 2-dimensional detector for GVAX or GSAX, and another one like point detector, even 2D. It could be to measure reflectivity. Then by changing simply position of the detector arm, we can switch between different type of measurements. And so then to get different type of information on our sample. So then all users, they use this, and we measure many different, or use many different techniques at the same time on each sample. So this is a bit of flavor how the deflector works. So then this, what you see here, turntable, it holds 2 crystals. So then this is, let's say, side view or top view. So then there is a beam. Then there is one crystal which deflect the beam back reflection. So usually what work, this is germanium 101. Then second crystal deflect beam back. This is germanium 220. So that this angle, break angle of second crystal should be bigger than the break angle of first crystal. And then it goes to the surface of the sample, and then in the point where this beam intersect with the initial beam, and then if we rotate this part as a whole solidly, so then we can change the grazing angle on the surface without changing the break angle on the crystals. And like this, we can change the scattering vector on the liquid surface, and then we can measure. Then here you can see several orientations of this RHD, what we call rotation. So the 0 angle, so then everything beam is in horizontal plane, so this is turned a bit on certain angle, and then this is 90 degrees. This is basically this orientation. So like this, we can quite fast measure the reflectivity. So here, this is very first measurement of X-ray reflectivity on liquid surface with this device. And then, for example, red line, this is scattering from water dots, and the blue line is measurement. This is just a calculation. Okay. And so then for this system, we can work with 2 setup. One is basic, what we call standard. This is this pair of crystals which deflect the beam, and then we can go up to 2.4 reciprocal angstrom. But now, recently, we learned how to use the same crystals and go to higher reflections, 3 times higher for each of them, and then we can expand the QZ range on liquid surfaces up to 7 reciprocal angstrom. So, which could be very interesting option for people who works on liquid metals, for example. So then about reflectivity, so if for somebody this is, let's say, new technique, so then what is going on? We have a beam going at a certain angle alpha to the surface, and then at the same angle, exit angle, we measure intensity. And in this case, as I told, the scattering vector perpendicular to the surface, and then this ratio between incident and the measured intensity, this is a Fourier transformation of electron density multiplied on the Fresnel scattering. And so by modeling and calculation, we can go from the measured curve to the structure. And then like this, from the periodic oscillations, we can know information about the thickness, about intensity, we can know information about distribution of electrons in the depths. So then how it nowadays goes at the beamline. So as I told that we have a attenuator wheel which manipulate with intensity on the sample and detector. And then from previous picture, you can see that intensity change many decades on the sample. So then this up to 10 power. So, but when we measure, detector cannot measure above a certain threshold, and then we change the intensity of the beam. And then this is what you see during the measurements. Automatically, so this is done automatically, intensity or position of the attenuator correspond to the position which is safe for the detector. It looks like this during the measurements. And then at each point, we measure now with the two-dimensional detector. And then on this detector, you can see this is the rest of direct beam, and this is a specular reflected beam. This is what we really want. And then we select several range of interest, like 1 for the specular beam and 2 for the background range of interest. And then through this formula, we can, and normalized on the attenuation of the filters, we can reconstruct the reflectivity profile. And then everything is done almost at the same time at the beamline. So then after measurement, immediately we can run the scripts on the Slurm, and then on the special machine what we have at the beamline, and then you have all the needed data right after the measurements. And here, this is a reconstruction of the reciprocal space map during the reflective measurements when we take all the intensities along the QZ direction and then we stitch them together. So this is additional information what we can get from the sample, not only the reflectivity curve, but also the diffuse scattering around that. So for the Grayson's diffraction, so if we have a two-dimensional system, so in a reciprocal space after the Fourier transformation, what is big became small, and what is small becomes big. So then we have instead of points, so we have a rods normal to the plane of the sample. And then this is in fact the break position if there is a two-dimensional ordering. And from this, we can learn information about 2D systems. So then from the position of these rods, we know what is the lattice parameters. From the length of these rods, we can see what is the thickness of this crystal in that direction. And from the thickness or width of these rods, we can see what is the correlation length of the scattering correlation length of these systems. If this is not really two-dimensional, but like a bit of third dimension appears, so then we can also see that on these rods we have some other back peaks which we can measure. So then we see information in the third direction how it is organized structurally, if this is a crystal. And then this is one example of real measurements. So this one picture is measured with two-dimensional detector, but we can also measure this if we want to have better angular resolution with 1D detector and the solar collimator or analyzer, and then afterwards we can see all these break rods to resolve them and then reconstruct the structure of our system. So then some words about the sample environments, which is very important for any type of experiments. And then in many cases, the users can come to us without their own sample cell if we have it. This also helps them during the experiment. And then we have different type of the sample cells to work at a liquid gas or liquid or liquid solid interfaces. And then one of the mostly used, this is a Langmuir trough. So then here you see this is a big area. In this direction, this is about 0.5 meter, and then beam goes to this liquid surface, and then we do all the measurements. Or we have also special language graph to work at a liquid-liquid interface. So this is language graph for that. So this is an example of the setup when we have at the same time measure on language graph with 3 detectors like reflectivity, diffraction, GID or GSAX, and also the fluorescence detector. So the 3 type of information we get from the same sample. We have also humidity cell, where if the people want to study how the films behave at the different humidity, so then we have also this type of the sample cell. Then we have some cells for the solid liquid interfaces. So this is an example, or we have a liquid interfaces with a fixed area layer. So we cannot change it, but for many cases, this is enough. Then we also have a special cell to study at a CO2 environment. So to go from the gas to liquid and the supercritical state at different pressures up to 120 bars and also temperatures up to 100 degrees. And so recently, so then already several years, we have another sample cell for CVD reactor to work on the liquid metals. So to use it as a catalyzer, for example, like a copper, and then to go to the materials on that. And then this is how it looks like in the experimental hatch. And this box is here to control the gas flow through the reactor and also the heating. So then we can use different gases, and the temperature is here about a bit less than 2000 K, what we can apply. And also for some other things, we have vacuumated chambers for samples. And also we have a chemistry laboratory close to the beam line, and then a lot of things could be also done here without the main SRF chemistry laboratory. So then going to scientific examples, so that I will start first with some study on liquid surfaces with the language graph, because this is mostly what we use with in-house and users. So then in this case, so when we have a language graph,
just 5 minutes as we discussed until.
Okay, fine, good. And so then here we can, from this type of measurements, we can see the break peaks, and from these break peaks, as I told, we can find what is the length of the molecule, what is the tilt, what is lattice organization. So then this is another more complex case where we study with all 3 techniques like the fluorescence, GID, and reflectivity. We see how with electrodeposition spray that nanoparticles, hydrophobic or hydrophilic, they can penetrate through the pulmonary surfactant. So this is a mimicked layers. So the measure with measurements of the diffuse scattering on the liquid-liquid interfaces. In this case, we can also study the elastic properties of the monolayers. So a lot of things what we are doing with in-house and also with external use, this is a 2-dimension nanomaterials, which is very important for many applications. And so here, this is a way when we apply simultaneously GSAX and GID measurements to characterize the growth of 2-dimensional nanocrystals in 2-dimensional crystals from lead selenide nanocrystals. And then with these measurements, we was able to characterize and give a model how the growth goes, but also with, as this is in situ measurement, we could find some other structures which is not possible to find with electron microscopy because you cannot pick up these crystals. So then with the CVD growth reactor, what I mentioned, so then here we can use the liquid copper or other metals as a catalyzer, and then afterwards with the different gases, we can grow the 2-dimensional films. And then here, for example, on this image movable, you see how the graphene flakes are growing, and we see this with our optical radiation microscope. And then we can, as soon as they grow, we can characterize to the reflectivity or GID for reflectivity. So as the surface in this case is strongly curved, we found a way how to anyway analyze this and reconstruct the reflectivity curves and then get information about the thickness of these layers, the interfacial roughness, the distance between the graphene layers and the metal, and then also we can measure diffraction. And here you can see that we see up to 3 diffraction rods from on liquid metal and this high temperature from graphene. And then if we change, for example, the substrate and not pure copper, but copper diluted with a gallium at a different proportion, we see that also this minimum, which correspond to the thickness or the gap of the layer above the liquid metal, we can see that it changes. It depends on the type of the substrate, and then this could be very important for the industrial applications to reduce the interaction between this graphene layer, for example, graphene layer and liquid catalyzer, and then for easy removable it from the surface. Also, the temperature can be reduced. So then another type of applications to show that we use some organic molecules to grow the organic frameworks. So in 2-dimension complex, and then afterwards even to grow second layer and make a kind of a woven between them and between patches, which makes these 2-dimensional crystals organic frameworks more stable, less brittle, and then more easy for application. Then at different time of this growth process, we can characterize with GVAX, in this case, the structures. So then another application, but this is a sample cell which comes together with users. So from Tübingen, that this is UHV machine with a beam epitaxial deposition, and then to grow some organic semiconductor crystals for photovoltaic, we can optimize the structure of this for the better performance for electronics, and then we can see that how structure change depending on deposition and temperature annealing. And also with the same group and a bit bigger, so that already with them we apply this machine learning algorithm which analyze reflectivity curve during the measurements, and then during the measurement it can see what is the thickness in this case of the film, and then stop the process growth when we reach needed thickness. So then in principle this can be also applied to get almost instantly the structure of the reflectivity curve after the measurements already fitted with these deep learning algorithms. So with the fluorescent technique, we can discriminate what is going on near the surface. And as I told, for example, here, it was some mixture of different ions in the subface. And then we can see that they sit at a different depths near the interface, they arrange. Or we can, for the some monolayers or multi-layers on the solid substrate, apply the, in this case, freestanding waves. We can see for how the system change. For example, this one is phospholipid DSPC monolayer. In one case, without the PEG, and another one is PEG lipids, and we can see is it inserting in between or not. And then from these measurements, we can see that it's mostly organized on the top, but not going in between the substrate, because there is no change in the fluorescence signal. And about Xania's measurement, what recently we start more and more often apply, so then we can see electronic states. And then in this example, we saw how the or we follow the zinc atom, and we see how this metal bind to the hemoglobin and how it change the coordination of the zinc depending on type of or pure solution or solution treated with a different ways of zinc. And so one of the recently also applied technique which we can use, but we didn't yet develop a lot at the surface part, but it is more going on the other part, coherent applications that we can use ourselves. Like here, this is for liquid-liquid interface, and then we apply this to study dynamic of the gelation process at the liquid-liquid interface. So then even coherent applications is possible on our side. And this is an example about application of CO2 sample cell to see how it affects on the polymer films, that they absorb, they change the thickness, and that even after we release completely the CO2, so there is a change of the structure, and also there is some rest of CO2 which is trapped by the system even at zero pressure. And this is also the same type of measurements, but with mesoporous materials, how they wash out from the pores, they wash out the surfactant. And then we can follow this process depending on the pressure of the CO2. So then this is briefly to finalize my then presentation, that here this is a list of the techniques what we can apply at ID10 surface end station. And also this is some characteristic what is available, flux, energy, monochromaticity, size of the beam. And at the end, I would like to thank you, first of all, and then also all the ID10 staff, and also the users of surface sketch and station. And I would like also tell you that now we have an open position of postdoc at ID10 surface. And then if anybody interested, or you know somebody who would be interested in this, so then you're welcome to apply at the SRF webpage. So then on this I will finish. Thank you.